Assalamu alaikum. Hi guys. Today I'm gonna finish the deflection of beams through the moment of area method examples. So let's begin. Actually, before we do that, I'm just not recreating. Actually, I took the same slide from the class before because these areas are going to help us in find the deflection using the moment area theorem. So we're going to use probably the last two today. So let's start with an example. So here I want you to find delta B and theta B for the beam below. This is a cantilever beam fixed at A. Okay, so we know that the deflection curve is going to be like that. But let's assume that I'm going to assume the wrong deflection curve. How would I figure out that the deflection curve that I'm choosing is the right one or not? Okay, so let's say I'm going to go with this deflection curve. So based on that, if I take a tangent at point B here, and then take the tangent at point A, then theta BA, which is the angle at B measured from the tangent at A, is this, and the vertical deviation from point B measured from tangent A is equal to delta BA. So now these are the two things that I'm going to figure out. So the first thing I need to do is to draw the M over EI diagram, and the moment is going to be simply WL times L over 2, which will give me a minus WL square over 2EI. Again, I'm drawing on the tension side, so this is negative and this is positive. So to find the theta, I'm going to start off with theta BA, which in essence is theta B, as you can see. So since the tangent at A is, or the slope at A is equal to 0, so theta BA here would be equal to theta B. So to calculate theta BA, I'm just going to take the area under the M over EI diagram, and it's going to be 1/3 L times minus WL squared over 2EI, and it will give me a minus WL cubed over 6 EI, indicating that the rotation is going to be clockwise, not counterclockwise. So theta B will be equal to WL cubed over 6 EI with a clockwise rotation. Okay, so I will move on and figure out what delta BA is. Now delta BA is the vertical deviation from point B on the elastic curve from a tangent, or measured from the tangent at A. And then that area would be 1/3 times L times minus WL squared over EI. Since it's about point B, then this is going to be 3/4 of L, and then this is going to be minus WL4 over 8 EI. Okay, so here what does the negative mean to me? And let's go back a little bit, and if you remember, we said if I have, let's say, delta BA like this, which is again the vertical deviation of the point B on the elastic curve measured from the tangent at A. So if B is above A, okay, we said this is going to be positive. Now if A is above B, then this is going to be negative. So since I have a negative value here, this is telling me that A is above B. Okay, so this is not the point A, and clearly here it is not above B. Okay, so which means that I've chosen the wrong deflected curve. Okay, and I'll just put that here again. So this is negative, means that A is above B. So for A to be above B, then the actual or the correct deflected curve should be this. Okay, so now then this will be my final answer. Here you can say that theta b, now here's the clockwise rotation, and delta b is now, which is equal to delta BA, is going to be WF4 to the divided by 8EI. So always remember this. If you're doing a deflection, delta BA, okay, this way is positive, meaning B is above A, and if it is negative, then A is above B. Okay, so from this you will know whether you've chosen the right or wrong deflected curve. Moving on to another example. In this beam, I want you to find the following. I want you to find theta at C, the deflection at C, and the maximum deflection. Okay, now I'm giving you EI here is equal to 17,556 kilonewton meter square, which means I want actual values and not in terms of EI. Okay, so now let's draw the things that we want to find. So first of all, I'm going to draw the deflected curve. As you can see, because it is not symmetric, then delta C is not the maximum deflection. So the maximum deflection is somewhere else. So again, this is my delta C. I'm going to take a tangent at point C. And then theta C is going to be the angle between the tangent at the point of the elastic curve with the undeflected chord or the undeflected shape. So I just took this here and then just moved it or moved it down. So this is now my theta C. Okay. So let's start by drawing the moment over EI diagram. This value 240 over EI is just simply the 100 kilonewton times 4 times 6 divided by L, which we used to call PAB over L. So this will give me my moment, the 240 over EI. Okay. So now, here I'm going to start off, with finding theta C. I could take the tangent at B, and I could take the tangent at A, but to me it looks more appropriate to take the tangent at A for this particular case, and then determining the angle theta CA, which is the angle of rotation at point C measured from the tangent at A. So what do you notice here? What we notice here is that this here is simply theta A, right? Which is the same angle here. So theta A, again, is measured from the tangent at A to the undeflected curve. So here I've noticed that theta A is simply theta C plus theta CA. Now, I still want to know, I can find theta CA using moment area theorem 1, and theta A I can simply find by finding the vertical deviation between B and A, okay, which is again point B being on the elastic curve measured from the tangent at A. Okay, so if I find delta BA, then I can find theta A. So again, theta A is equal to theta C plus theta C A. I'm going to find delta BA first. Delta BA is going to be equal to, again, now here I'm going to take the moment under the EI diagram, and again it's about point B, so this is going to be 1/2, which is, again, let me draw the triangle of the moment so that we don't forget what it is. Okay, here is my 240 over EI. So now this would be equal to, this is now going to be 1/2 times 4 times 240 EI times 1/3, which is now this distance right here, times 4 plus 6, plus the other triangle, which is going to be 1/2 times 6 times 240 over EI times 236, and this is going to be equal to 6,400 over EI. So theta A is simply delta BA divided by L. Again, going through that whole tan theta is equal to delta over L, with tan theta is so small equal to theta A, then this will give me theta A to be equal to 640 over EI. Right? Now, theta CA on the other hand is going to be the angle, or it's going to be the area under the moment over EI diagram between point C and A. So technically speaking, we're just talking about this triangle right here. So this now is going to be equal to 1/2 times 4 times 240 over EI, which is going to be 480 over EI. So theta C now is going to be theta A minus theta CA, and that's going to be 160 over EI. Now I'm going to substitute for EI by its value of 17,556 to get 0.0091 radian. Okay, so this is now my theta C. All right, now let's move to the second part, which is finding delta C. Now again, here I only can find, using through moment area theorem, delta CA, okay, but I cannot find delta C directly. But again, having found theta A, okay, then by using the same technique in which theta A is going to be equal to delta C plus delta CA divided by L, or theta A times L is going to be equal to these two. So stating this equation, theta A times 4. So now I'm just going to be dealing with this part of the moment over EI diagram. Again, let me put that down again. So now theta A times 4 is going to be equal to delta C plus delta CA. Again, this is the vertical deviation from the point C on the elastic curve measured from the tangent at A. So the only thing you have to find now is delta CA. So this is going to be, again, moment about point C. So this is going to be 1/2 times 4 times 240 times 1/3 times 4. Again, moment about point C. So this is going to be equal to 640 over EI. Then delta C, the value that I want, is going to be 4 times theta A minus 640 over EI. It's going to give me a value of 1,920 over EI. Again, since this is the last thing to find, now I'm going to substitute over EI with 17,556, and the final answer would be 109.36 millimeters. As I said, always leave the substitution of the value of EI to the very end. If you do it at the beginning, the values are going to be very messy, and the chances of you making mistakes will be greater. Okay, now let's move to the tricky part, which is finding the maximum value. All right, now here I'm going to make the assumption that my maximum value is after point C. Okay, again, this is an assumption I'm going to make. To me, it looks like the right assumption, but again, and I will talk about this at the very end. So we know from previous class, if we have maximum deflection, then the tangent at that point is going to be, or the slope of that tangent is going to be equal to 0. So I'm going to call this tangent max, which is the tangent at the maximum point. Okay? Now, here, if you've noticed, I'm going to now find delta AB, or actually I'm going to find theta B. Why? Because I'm going to use the same technique that I used in the previous part, but again, I need this angle to be able to find this whole distance from this point to that point. Okay, so okay, now this distance here is delta max b, which means it is the vertical deviation between the maximum point at the elastic curve measured from the tangent at b. And this value here is going to be delta b max, which is the vertical deviation of the point B on the elastic curve here, measured from the maximum tangent, which is this. Okay, so why? So what you've noticed that delta B max, as we shown in the last class, is simply delta max. Okay, now you would tell me, so if I know delta max equal to delta B max, so I can use the second area theorem, right? And you would be correct, but my problem is I don't know where maximum value is. So this is going to be at some distance x. Okay, so how will I find x? Again, theta b times x is going to be equal delta max, right, plus delta max b. Again, I don't know what delta max is, but I know how to get it. So that's going to be simply delta b max, right? So now theta b times x is going to be delta b max plus delta max b. So I'm going to take the moment about point B for the first part and then take the moment about the maximum point for the second part. Okay, so here the only unknown is x. So let's start first of all by finding theta b. So theta b, I'm going to get that from delta AB, which is the vertical deviation from point A on the elastic curve measured from the tangent at B. And again, here I have the, let me redraw the moment diagram. So again, this is 240 over EI. So delta AB is going to be 1/2 times 6 times 240 over EI times 1/3, 6 plus 4. Again, I'm taking the moment about point A, plus the other triangle, this one, 1/2 times 4 times 240 over EI times 2/3 times 4, and the answer would be 5,600 over EI. Then theta B is going to be delta AB over 10, and it's going to be 560 over EI. So far, so good. Okay, now let's find delta max B again. Now here I'm going to take the moment about the maximum point. So I'm just going to give you a hint. So if I have any triangle, okay, and let's say the maximum ordinate is W, and this distance is, let's say, L. So, and I want the value at any x for this triangle, then this slope right here is going to be the maximum ordinate W times x over L. Okay? So, if I go back now to my situation, so this is point x, okay, the max, and it's going to be at some position here, right? So this value here is going to be, what's my maximum ordinate? 240 over EI, so that's my maximum ordinate, times x, right, divided by, what's the total length? 6. So now this is this part right here, x now being this distance, okay, so the area would be 1/2 times this distance times this ordinate. Now times again the moment, and that's going to be about the maximum point, so this distance from here to there is going to be x over 3. Okay, so again it's going to be 1/2, and here's my x over 3. So delta max b is going to be 1/2 times x times 240x times x over 3. I'm going to get 6.67 x cubed over EI. If I want now the moment about b, still 1/2 times x, still 240 over 6 EIx times 2/3 x over x. Now, and this is going to be 13.33 x cubed over EI. So now I can use this equation in which I'm going to say that theta b times x, which is 560 over EI times x, is going to be the addition of these two, which is going to give me 20 over EIx cubed. So the only unknown here is x, so x is 5.296 meters. And since this is less than 6, so my assumption is correct. Have it giving you a value more than that, or something not meaningful, like maybe a negative value or something, then you know that your maximum point is not from B, and it's instead from A. So delta max now would be simply equal, again, because we said delta max is equal to delta B max, so this is, which is 13.33 x cubed. So it's going to be 1975.5 divided by EI. So the maximum value now is going to be 112.5 millimeters. And that will take care of this example. Now to our last example. In that example, I want to find theta c and delta c. The main point of this example is to show you how to use the moment superposition. For the last couple of examples, we only dealt with one moment diagram, or let's say not one, with a simple m over ei diagram. So now if I'm going to draw the actual m over ei diagram for this question right here, again, I'm going to use my technique, which is 70 times 2. This is 140 over ei. Then I'm going to do this line, and then I'm going to go down WL square over 8, right? WL square over 8 here is going to be 40 times 25 divided by 8, and it's going to give me 125 over EI. This value here is minus 70. Again, I'm drawing the negative up and positive down tension side. So this is going to give me 55 over EI. Okay, so what you've noticed, I've completed this triangle, and then I took from it the WL square over 8. Okay, now if I want to use this area for my calculations for theorem 1 or theorem 2, you will find it is very hard to find the area of that one unless I'm using some sort of an integration. So for this, I'm not going to do that. Instead, I'm going to use the moment superposition that we've talked about earlier, and this is going to be transformed into that. Okay, so now this, I know the full area of that, and I actually know where the location of the centroid is, as I do know for these two as well. But I did not draw this in vain, because I also need to know how the deflected shape would look like. So I would know this would be concave up, and here's my deflection point. So this is going to be probably something like that. So based on that moment, this is now my deflected shape. You would argue that your deflected shape might go like this and maybe stay 0, okay, or might go up a little bit. You might be correct, but me, I don't think so. But then again, I really don't care, because I'm going to use the same technique of finding delta with some tangent and see if whether this is correct or not by using the same trick. Okay, which is, like I said, in general, if here I'm probably going to use delta CB, for instance, or delta C, I'm not sure. But again, going this way, CB above B is positive. If B is above C is negative, and we're going to test that out here again. So now, I'm going to draw the tangent at C and the horizontal at C, showing that this is my theta C that I want, and then this is my delta C. As you can see from this, there's really no direct relation to find theta C or delta C, so I have to refer to some other tangent. The closest to me actually is theta B, So I'm going to use the tangent at B. For that, I can find the angle theta B. Okay, again, I'm using the same technique. I'm going to use delta AB. So delta AB, again, is point A at the elastic curve at A measured from the tangent at B. And theta B now would be equal just delta prime, and theta CB, I can find that out quickly. So from that, now it's a little bit different. Here you can see now that theta C is equal to theta CB plus theta B, while delta C is equal to delta prime plus delta CB. Now this I'm going to find from theta B, and this I'm going to use the moment area theorems, and theta C is just going to be the addition of these two angles. So let me first of all try find theta B. Now theta B is going to be equal to delta AB over 5, right, the length, and I'm going to take that length out and just find theta, delta AB first. So that's going to be now equal to 1/2 times 5 times minus 140, remember, and hopefully I'm not destroying that too much. Let me use a different color for the moment. So again, for this part, I'm going to have to use this part of the moment, this triangle right here, which is 140, and I'm going to use this moment diagram, which is 125. So now, so this is again the 1/2 times 5, again use the negative value as is because this is negative, 140 over EI times 2/3 times 5 because here I'm taking the moment about point A. For this part right here, this is going to be now 2/3 times 5 times 125 because this is a positive value over EI times 2.5 because this is exactly in the middle, and this is equal to 1/5 minus, so this value is negative. So what does that mean? It means B is above A. So now this part, or actually this is telling me that this part of the deflection is actually correct since B is above A, and hence I got the negative value. Okay, so this deflection curve is correct. Now moving on to theta CB. Theta CB again is the area between C and B, which is this area here, which is only, let me draw that in a different color as well. I'm going to only be dealing with this triangle right here. Okay. Again, this value is 140 over EI. Let's go back to red. Then theta CB is going to be 1/2 times 2 times 140 over EI, which is going to give me a value of 140 over EI. So now theta C, again, which is this whole thing right there, is going to be the addition of theta B plus theta CB, which is going to give me 165 over EI. Now delta CB, on the other hand, is going to be 1/2 times 2 times 140 over EI, again negative value, 2/3 because this is now the moment about C, and the value is 186.67 over EI. So since it's negative, then B is above C. Again, this is correct here. This is the tangent at B, and this is the value at C. So again, my deflected shape is correct. Had you chosen to go in the other direction, saying maybe that somehow this is going to be, let me choose a green color, it's going to be something like this, then this will tell you no, your choice is not correct because this value is negative. Okay. Then delta prime is simply 2 times 25 over EI, which is my theta B. It's going to be 50. Then the delta C is equal to 236.67 over EI. And my deflection is going to be 13.48 millimeters. So this finishes the moment area method. You guys have a nice day. The next class will be on the conjugate beam method, and you guys stay safe and have a nice